So we are talking about derivative rules some more. Last class, we kind of went over the core idea and we got to that power rule. This one here, that was the final thing that we got to in the last class. And from this class, we'll see some just practice with that. We have two more derivative rules that we are going to learn. And then we will see various applications. The first thing we'll look at is going back to minimums and maximums, which we've already talked about finding visually, but now we'll use the derivative rules and see how we can also find those points and learn things about them using that. All right, so let's just do some quick review here with what we talked about last time. If you remember, we are talking about tangent lines. So we have some kind of curved function, like this thing here, our y equals x squared, and we have some points there, which we said could be this thing. And we want to find what is the slope of the curve at that one point. So it's represented by this line, again, tangent line that touches the curve at exactly that one point and only that point. But how can we find that mathematically? How can we find out exactly what that slope is? So that's what we saw last time, that process to slope formula here. So this is where our whole idea of derivatives comes from, just our delta y over delta x are, let me show this. So we said we're going to draw a second point on our curve and make sort of an estimate red line for the blue one. And then the coordinates for that point we've defined here. So the slope of that red line is just y2 minus y1 over x2 minus x1 with that h representing our delta x. And we're just going to make that h closer and closer to 0 until it basically becomes exactly 0 using a limit here. And that will give us this perfect estimate for exactly what the slope of that red line will be, or tell us it will always be what the red line is, and then that will give us our perfect estimate for the blue line as well. All right, and we did all of this for this function, x squared, and we got this result. We did our long version of the derivative, and we discovered that if our original function is x squared, y equals x squared, then our derivative function, which we write like this and read as f prime of x, or y prime, equals 2x in this case. So 2x is also a function. It's also a thing we can put on a graph and visualize. And that's what we have with this blue line here, the original one in orange. So this whole thing, this new version of our function here that tells us slope, that's the derivative of the original function. And we did some practice looking at this thing and finding some point here. Let's choose any point on the original function and say, what exactly is the slope at that point? What is the slope when x is equal to -2? -4. So we just take this point here and we line up vertically. So just draw a vertical line down until we hit our derivative function. That point right there, y value is -4. That's the slope. Or we could just take that value of -2 and substitute that in here for this x. 2 times -2, -4. So we can use this derivative function here or look at our graph. All right. So with your class, I forgot to do this last part here. We did this. We found the derivative for this function. Do you remember what it is? Okay. So 12, I'll just write our rule here. So it's 4 times the exponent here, 3x, and then our exponent 3, we subtract 1 from it, which is just 12x squared. Okay, so that's the general version of our derivative for this function here. And what about at this point? When x is equal to 3, what is the slope? 108. All right, so our slope then, we want f prime at 3 when x is equal to 3. So we just substitute in that number. 12 times 3 squared, 12 times 9, 108. So if we want the slope for any point on this function, not too hard. We just take our original thing here, find our derivative, and then substitute in the x value and see what we get. And that will be the slope. Okay. So this, what we used here is called power rule, which is this here. So if our original function looks like this, y equals ax to some exponents, then our derivative will be y prime is a times n, the value of the exponent, and then you just subtract 1 from the exponent there. That's it. So we spent an entire class last time just getting to that little shortcut rule. There are lots of rules for derivatives. This is kind of the most, I could say the most important one. There are lots of others too, but they all come back to this thing eventually. Okay, so let's try the first one here. So if y is equal to 10x cubed, what is our derivative? Okay, all right, so I'm just going to write this with a little extra detail this first time. So our y prime, we write our derivative with this little prime symbol here. Y prime is equal to 10 times 3x, and then 3 minus 1 for our exponent, so 30x squared. So for this function here, any slope on that curve is given by this function here. Okay, so you guys can do the next two. Go ahead. All right, we're ready. What's the first one? So y prime, let's practice reading the left side as well. Y prime is equal to 4x. Cubed. So okay, we'll just jump straight to the final. We're not going to write the -1 every time. So 4x cubed. Done. What's the next one? Okay, tell me the left side first. So p prime. Okay, 5.2 q 1.6 there. So it's not y and it's not x. That doesn't matter. The p is the one that's separate, so we treat that like our y. Q's the other one, treat that like our x. So it doesn't matter what the letters are. All right, 2 more here. All right, let's take a minute. I know the fourth one's not too hard, but the 5th one will take just a moment. So try that out. All right, looks like people are ready. What is our 4th one here? C prime equals to Q. And our last one. Actually, before we do the derivative, let's just make sure we remember our rules about negative exponents. If I want to rewrite this, no derivative yet, just rewriting this, but I don't want a negative exponent. How can I which one? Okay, 5 over Q. So negative exponent just means 1 over that thing. Okay, so that's how we could rewrite it, but it's much easier to use power rule when we have it as a negative exponent. So our derivative would be C prime equals -5 Q -2. Okay, and again, let's say I don't like the negative exponent. How could I rewrite this? Okay, so -5 over Q squared. There's our derivative. So sometimes we will need to do this and convert from sort of a fractional thing to a negative exponent and then go back. Just remember our exponent rules. We should be able to handle that. Okay, so there's some basic practice with power rule. Good. All right, so there are lots of ways of writing derivatives, and we need to be familiar with all of them. So if we have some basic function, y equals, or y or f of x or whatever, then lots of ways we can write our derivative. We've seen these ones so far. So just y prime for f prime of x, both of those are possible. But we have 2 more ways which I know looked a little more confusing or overly complicated, but they are useful for later things in calculus. First one here, so dy over dx. This is how we read it on the bottom. Or more formally, the derivative of y with respect to x. That's this thing here. So this is not a fraction. If this is your first time seeing this, you might think, well, d divided by d. No. Just exactly this form means derivative. Okay, so just memorize this whole thing as a little block here. And same idea, but as this f of x notation, just d over dx of f of x, that's kind of the thing that's on the top there. Again, not a fraction. All 4 of those things mean the exact same thing, just derivative of whatever function. So different teachers, different textbooks, different whatever, they're all going to use different versions of this or mix them all. You need to be familiar with all of them. When we do partial derivatives for multivariable calculus, which we will not do in this class, that's a later thing, and this dy over dx notation actually becomes very useful. So that's why I'm showing it to you now. Okay, so that's the notation. Got 2 more rules to talk about. The other two are really not that hard at all. So the first one says if your function actually has two different parts, two different things added together, then the derivative will be just the derivative of the first part plus the derivative of the second part. So just basically do the derivative separately and then add them back up afterward, and that's it. So very easy rule here. So like this, x to the exponent 6 plus x to the exponent 4, our derivative is just derivative of this thing, 6x to the exponent 5, and the derivative of this thing, so 4x cubed, and then just add them together afterwards. That's it. Okay, so doesn't have to be very complicated here. Let's take that rule, and there are two examples here. Please try to solve. Are we ready? Yeah, okay. So what's our first one? Y prime equals 4x plus 3. So the x is disappearing here. So if we had 3x, our derivative, then we always have a little exponent of 1 there. So derivative would be 3 times 1x to the exponent 1 minus 1. That's x to the exponent 0. That's just 1. So if you have any variable with an exponent of 1, it's just going to disappear. Okay, so that's the short version of it. So 4x plus 3. That's it. Our other one here on the left. What's our left side? Okay. So AC prime, don't get confused by the two letters here. This is for average cost, so it's one brackets, which part? We could do that. I don't think it's necessary. In like economic stuff or finance stuff, you're going to see, just like we had TR and TC and stuff, and we'll have marginal revenue and marginal cost and average cost. There's lots of these that we're going to see. Like TR is total revenue. It's not two numbers. It's not two variables. It's just one thing. Okay. So that's the same thing happening with AC here. We could put the brackets around it, but you are not going to see economics textbooks do that. They just expect you to remember it's one concept, not two, so no brackets. Okay, so brackets are fine. I'm not going to put them in because I want you to remember and recognize that this is one concept here. So AC prime equals 5 plus or minus what's on the top of the fraction? 4 or 2 over q squared. Okay, let's just take a moment and think about how we got that. So 2 over q, that's equal to 2q to the exponent -1. And if we take a derivative of that, that's negative 2q1, negative 1 minus 1, that's negative 2. And then we just rewrite that as negative 2 over q, now positive 2 exponent. So if we have, again, these fractional exponents, you have your variable on the bottom, change it to a negative exponent, use power rule, and then you can change it back afterwards if you want. Good questions? All right. So last rule that we will talk about is this one, constant rule, which is probably the easiest, which says if your function is just a constant, not a variable, just some number, then the derivative is just 0. So 2 more examples. Please try these ones out. Are we ready? Yeah, okay. What is our first one? Y prime equals 2x plus 7. Okay, so like we saw before, 7x exponent is 1, so the x is just disappearing here, and the 5, that's, you know, like we could write plus 0, but we don't need to. So just 2x plus 7. That's our derivative. All right. For the one on the right here, f prime of x. Okay. Negative 3 minus 1.5. Negative 0.5. Okay. All right. So negative 3 minus, we have our coefficient 3, and we have our exponent there is 0.5. So 3 times 0.5, 1.5. Negative sign out front, that still stays there. So negative 1.5. And then our exponent 0.5, just subtract 1. And we get that negative 0.5. So let's do some kind of rewriting or some simplification here just to see if we remember our exponent rules. So negative 3 minus 1.5. Let's convert over. Okay, so let's do 2 steps here. So changing our exponent to be positive, so 1 over that thing, and it's 0.5, so that's 1 over 2. Let's say I don't like that either. I want that as a root. Okay. So negative 3 minus 1.5 over root x, square root of x. If we could, if we don't like having the root x on the bottom, then we could convert the fraction over. I'll leave that step, but just kind of showing us some of what we can do to sort of simplify our exponent there. Okay. So there is our constant rule. That's our third rule. That's all we're gonna need. There are a lot more derivative rules, product rule, quotient rule, chain rule, all kinds of stuff. We will be able to get a lot done just with these three rules. So we're gonna focus on these ones for our purposes in this class. So that's the three. That's enough for us to do lots of different stuff with our total cost and total revenue and find those maximums and all kinds of stuff. Questions about these rules? All right, so let's go back and talk about turning points again, but now with our knowledge of derivatives and what we can see about them. So two types of turning points, as we've been talking about. We have our minimums and we have our maximums. So let's just remember, at the bottom, at the actual minimum point here and at the maximum point here, what is the slope? 0. So if we drew a tangent line would be like this or like this, and the slope would be perfectly flat. It would be 0. So at those points, at the minimum point and at the maximum point, what should the first derivative be equal to? 0, because first derivative is the slope. That's the thing that tells you the slope. So at the minimum points and the maximum points, first derivative should be equal to 0. So this is our method. This is how we will mathematically find exactly where those minimum and maximum points are. We find our first derivative and then solve it for 0. Find the zeros of that function. That tells us the exact location of these turning points. However, we do have a third type like this, and we have talked about this a little bit so far, where slope does go exactly to 0, but in this case, before that point, slopes are positive. After that point, slopes are positive, so it's not a turning point. But here also, if we found the zeros of the first derivative, then this would look like a turning point. So we need one more thing to tell the difference between them, and that is going to be second derivatives. I'll talk a little bit about them today and then a lot more about them in our next class. But for today, this is all we need to know. If the second derivative is greater than 0, you have a minimum point. If the second derivative is less than 0, you have a maximum point. And if your second derivative is exactly 0, you don't have either. You have this kind of false turning point, and it's not actually a maximum or a minimum. So those are the three possibilities that could happen, and we need to remember those things so we don't get fooled by our first derivative. All right, so that's our process, and we're going to do a bunch of examples of exactly this, finding zeros of the first derivative and checking the second derivative. So let's do those here. We'll do the first one together, and then I'll give you a moment to try out the second two. So turning points for each of these functions here. So the process, I'll say it again, we're going to find the first derivative, set that equal to 0, solve for the x's when that thing is equal to 0, first derivative. Then we're going to check it in the second derivative. Those are the 4 steps. We're going to do that a whole bunch of times today. So first step, first derivative, y prime equals 6x minus 18. All right, very easy. Set this equal to 0. So y prime is equal to 0, or when it is equal to 0, we have 0 is equal to 6x minus 18. Solve for x. All right, also very easy. X is 3. Not quite. We need the second derivative. Yeah. Okay. So second derivative in this case is what? 6. So this is our first time seeing this. So I'll just explain a little more. Second derivative, all you do is take the first derivative and then do the whole derivative process again. Exact same thing. 6x minus 18. Derivative of that is just 6. This is what we look at. Is this positive or negative? Okay, this is positive. What does that tell us about this point x equals 3? It is a minimum point. Okay, so this thing is greater than 0. So therefore, this thing is a minimum. Think back to what we talked about with the leading terms. This leading term is a positive x squared. So the shape of this function we know should look like this. So minimum points, that makes perfect sense with what we know about the shapes, okay? So the visual stuff we did last week and the derivative stuff we're doing now, 2 different things giving us the same information, okay? All right, B and C, go ahead. Give people a few more seconds to work. Okay, let's take a look at the second one. Let's do our visual thing first and see what we can notice. What is the leading term? Okay, so we have a negative x squared. What does that tell us about the shape? Okay, so shape should look like this. So we should have how many turning points? 1 turning point, and it'll be at the top. So it should be a maximum. So we'll do our derivative stuff, and hopefully we get the same result. All right, so what is our derivative here? Minus 2x minus 1. So here, minus x. So the exponent is 1. That turns into 0, so that part's gone. But don't forget that we have coefficient of 1 in front. So derivative of x is just 1. It's not 0. It doesn't disappear. All right, so first derivative is this. Set this thing equal to 0. So when y prime is equal to 0, that means 0 is equal to negative 2x minus 1. So x is equal to, all right, negative 1 over 2. And then we, right, second derivative of this thing, y double prime is equal to negative 2. And this is less than 0. So based on our little chart up here at the top, we are dealing with a maximum point. So again, exactly what we were expecting from our visual understanding of these functions. All right, and one more here. So y prime equals -1 over x squared, like this. So just remember, we could rewrite this as 1x, the exponent's -1, and then -1 times 1, -1, and then our exponent subtracts 1. Okay, so we have this thing, and set that equal to 0. So 0 is equal to -1 over x squared. Okay, impossible. So here, just look at, we can just easy way to see that this is impossible. If our x value is anything positive, then the result will be a positive number. It's, sorry, negative number, because the negative on the top, and our result will not be 0. If x is any negative number, squared, it's going to turn into positive, -1 on top, still negative number, not 0. Only other possibility, x is equal to 0. Division by 0 problem, can't do it, so we have no solution here. No solution. Therefore, what do we know about turning points? No turning point. No turning. Just like what we saw in week 3 when we are trying to solve for the intersection point of those parallel lines. If there's no solution, therefore you find kind of a math problem like this and there's no solution, that means that thing doesn't happen. No, the parallel lines don't intersect. Here, we just don't have any turning points. Okay, so process again, I'll say it again here. First derivative, find the first derivative, set it equal to 0, solve for x when it's equal to 0, check in the second derivative. Everyone remembers that process? Yeah? Okay. Do it again. If you think you have the answers, you can write them in the chat. You're finished? Tell me what you think the answers are. -2, -1, and 3. Okay, so 3 turning points, and you think it's those 3. Okay, so -2, someone said -4, someone said +2. Okay, that's been a fair bit of time to work, so it's a little bit harder for a few reasons. We'll look at that. Okay, before we do the derivative stuff, let's think again visually what we understand of these functions. Leading term is -x³. So how many turning points could there be? Think of the shape. Look, x³. x³ has 3 possible shapes. We could have this, or sorry, this is negative. So we could have this, we could have this, or we could have this. In the first one, how many turning points do you see? 1 and 2. Second one, how many turning points? 0. This would kind of look like a turning point, but it's not actually. So not there. And here, how many turning points? No turning points. Turning points are where the slope is changing from positive to negative or negative to positive. Here we have 2. Here we don't have any. Okay, so the number of turning points that are possible, 2 or 0. 2 or 0. There cannot be 1, cannot be 3, cannot be 5. We have 2 turning points or we have 0 turning points. One of those 2 things. All right, so let's do our derivative here. So y prime is equal to what? Yep. Plus 18x minus 24. We set this equal to 0. 0 is equal to -3x squared plus 18x minus 24. All right. So solving for this, solving for x is a little bit harder. We have a quadratic here. What are we going to do first? Okay, so common factor, I'm going to take out the -3, the whole thing. So -3, and then what will we have inside? X squared plus minus 6x plus 8. Okay, so all right, we factored out the -3, and now we have a coefficient of 1 on the x. That's very nice because it lets us do the sum product method. 2 numbers that add to -6 but multiply to +8. What numbers could that be? 2. Positive or negative? 2 plus 4 equals -6?
-2 and -4.
Okay, that's coming after. First, we're just factoring. I just want the two factors. Okay, so -3 and then x minus 2 and x minus 4. Okay, yeah, you were thinking one step further. Yeah. Okay, so this here, let's confirm this result. So in case we're not convinced that this is the right thing, we can just very quickly check this. X minus 2, x minus 4. So take the first term, multiply it by both of the other things, x squared minus 4x. And then the second term, multiply it by both things, minus 2x. and positive 8, negative 2 times negative 4. And just simplify minus 6x plus 8. Okay, that's the same as what we started with, so the factoring is correct. It's always easy to check our work like that. All right, so from here, so all of this equals 0. Let me just write that out here on the side again. 0 equals 0. So we have 3 things here being multiplied together, and the result is 0. So at least one of those things must be 0. The negative 3 is obviously not 0. So the only possibilities then are that x minus 2 equals 0, or x minus 4 equals 0, and I've kind of run out of space. So x equals 2, or x equals 4. So those are the 2 turning points here. Those are the 2, or sorry, those are 2 possible turning points. We should be checking them with our second derivative now. Okay. So mostly done. Second derivative is what? Negative 6x plus 18. Okay, so in the previous examples, we had just a number, but now we have this function. So what are we going to do? Okay, so the x values that we got here, so x equals 2 and x equals 4, we are going to sub both of those into this thing separately. So we have y double prime equals negative 6 times 2 plus 18. And we also have y double prime equals negative 6 times 4 plus 18. What's this result? Positive 6, and this one? All right. All right, negative 6. So this one here, this is positive. So what do we know about this x equals 2? Minimum. Okay, so x equals 2 is a minimum point from this. So x equals 2 is a minimum, local minimum. And then the other one here, okay, so this is a negative value, and we've said if y double prime is less than 0, we have a maximum points at that spot. Okay, so let's think about our graph, our function one more time, what it looks like. So it looks like we have this thing. The right side is going down, left side is going up. And what these results are telling us is we have a minimum point first and then a maximum point second. Minimum first, maximum second. That perfectly matches what we expect the shape of the graph to be. So 2 different things telling us the same results. Looks like we got it all right. Okay, so this is where things get a little more complicated. Sometimes we have to do some kind of solving of a quadratic or whatever to find the x values, but still possible. Again, this whole process here, sum product method or quadratic formula, whatever you want to use. In the workshop last week, I went over a bunch of practice questions about exactly this, solving quadratics. So you can go back and watch that. Questions? Okay, so that was a whole lot of talking there, a whole lot of work. Let's just wind down, relax a little bit. All right, give people a moment. I'm going to erase this I hope everyone has everything written. So let's come back to our graphs. This graph here is exactly what we were just dealing with, the negative x cubed plus 9x squared, et cetera. So we just solved it, right? So looking at the graph, where do you see, or first, how many turning points do you see? 2. Where are they? Okay, so when x is equal to 2 and when x is equal to 4. Exact same thing that we just got from our whole derivative process. Okay, how many intervals do you see? 3. All right, so we have going down, increasing, and decreasing again. Okay, good. So let's take this and now we'll add the graph of the derivative that we, again, just found. First derivative will give us this. Okay, so like we did before with the x squared and the 2x, we're going to kind of look at the two, compare them, and see what we can notice about these, what connections we can notice. So first, at these turning points with our original function, the blue one, what is happening with the green function, the derivative? 0. So right there. So again, the turning points mean your slope there is exactly 0. The derivative is the thing that tells us the slopes. So the derivative should be 0. And again, that's exactly what we see here. Okay, so that's first this very simple level kind of connection between the two. Turning points of the original, zeros on the derivative function. So that's here. Next, we can do a little bit more. Let's look at this middle part here between the two turning points. What is the original function doing over that section? It's increasing. So it's going up the whole time. What is the derivative function doing over that interval? Okay, yeah, so it's partly increasing, then partly decreasing. But so that's a separate thing. What is true about the derivative function for the whole thing? There's something that does not change about the derivative function in this area. Yeah, it's positive. Okay, so all of this here, these slopes are positive, positive, positive slopes, right? Some at the beginning, they're just slightly positive and then a bit larger and then closer to 0, but they are positive the whole time. Again, the derivative is the thing that tells us the slopes. So the derivative should be positive. The y value should be positive the whole time. We do notice, as you guys were mentioning, we do have kind of this maximum point here. So that's probably going to be kind of the most positive possible point of our the largest slope, most positive slope that we have in this middle area. But that's about second derivative. So we're going to come back to that a bit later. But let's also just notice on the outside here, the original function in this interval is decreasing. What do we notice about the first derivative? Okay, so the connection here, it's negative. That's our connection. So decreasing means slopes are negative. So the y values of the first derivative here are negative. So the increasing thing is not a consistent relationship because over here, original function is also decreasing, but here all the slopes are negative. So the connection is that it's the y values of the first derivative are negative on those two outside intervals. Okay, so that's the relationship. And that as well, I have written here. I original function is increasing, first derivative values must be greater than 0. If the original function is decreasing, first derivative values must be less than 0. But what we're actually going to do is go the other direction. What's our original function doing? Well, let's just check the derivative, and that tells us if it's increasing or decreasing. All right. So this one as well, just like the x squared and the 2x graph, I have, the answer, like the connections written here on the left. But if you can't see that yet on the graph, keep staring at this graph after class until you see that and you can kind of feel the connection between the two visually here. So what is the original function doing? How does that relate to the y values of the first derivative here? So keep looking at this until that makes sense. We're going to add another layer of complexity next week, which is the second derivatives. So if this doesn't make sense to you, then those other later ones will also not make sense. All right, we got some more time. I have, or just quick little preview. The thing that we will talk about next week with the second derivatives is this idea of curving up or curving down. And I'll say lots more about that in the next class. Okay, let's do a little more practice. I got these two here. Find the turning points of both of these. These will be the last examples today. Before you start the derivative stuff, it might be a good idea to just look at the leading terms and know what you should be expecting, and then make sure you get the same results with your derivative. Tell me what you think. -2, turning point, okay. All right, it's been 4 minutes. Let's try these out. First one, what is our first derivative? B prime equals 4q plus 8. Set that equal to 0. So 0 is equal to 4. Q plus 8. Q is equal to -2. Okay, so second derivative, p double prime is equal to 4. So okay, yeah, so I know you think positive number means big, so means maximum, but it's actually reversed. Remember, this function here looks like this. It's a positive something squared, should be a minimum. Okay, so this thing is greater than 0, so this thing is a minimum, exactly 1 minimum point. All right, next one. We have first derivative here is what? 2, sorry, no, not 2. 3 squared minus 6x minus 9, set that equal to 0. 0 is 3x squared minus 6x minus 9. So, okay, so we'll factor out the 3 here. We have a common factor of 3x squared minus 2x minus 3. And we can use sum product method here. So two numbers that add to -2 multiply to -3. Right, so 3 and then x minus, we have those order, right? So x plus 1, x minus 3. Let's just double check that. So +1 times -3, -3, that works. +1 minus 3, -2, okay, that works. So our two solutions here. Okay, so if x plus 1 is equal to 0, that means x must be equal to -1, or x must be equal to +3. So I'm skipping a few steps here because we've done them a bunch of times already. There are the 2 points. Let's move all this over a bit. And our second derivative is what here? X minus 6. 6x minus 6. Okay, and we're going to take these two values for x and substitute them in. So let's just label these properly. Okay, so when x is equal to -1, then y double prime is equal to 6 times -1 minus 6, which is -12. So therefore, this is a maximum point because we have a negative number there, and then the other one, when x is equal to 3, y double prime is equal to 6 times 3 minus 6 is +12. So here we have a minimum points. So again, all of these make sense with what we can expect from the graph. This was a positive x cubed. So this kind of pattern is what we were expecting. We had a maximum point first, minimum points second. Okay, that matches what we expect to see from this graph. Give people a moment to write if they need it. Good. All right, going to erase. Now we have more, but those are for next class. Don't worry. So this is just kind of a summary of how we're using derivatives. I've been talking about this all class, so I won't repeat it. But if you want to come back and look at this later, then it's here in the recording. Right. So derivative rules. Sorry, derivative notation first. 1, 2, 3, 4 things that all just mean find the derivative. And then we have 3 different rules. We have power rule, sum rule, and constant rule that we have been using. So these 3 rules you need to remember and be ready to use. What else? We talked about that already. The homework questions, they're posted. You saw them already. Just in case it's hard for you to read them like typed out, then here's the same questions, but with nicer formatting. So take your screenshot or whatever. There will be a preview question. I don't have that posted yet, but that'll be ready soon. This evening will be another workshop, and it's not going to be about the maximums and minimums. It's just going to be reviewing the core idea, kind of the definition of the derivative, and like that long version that we did in the previous class, and also just using those derivative rules, power rule, product rule. So just lots of those. Okay, so that's what the review is going to be. In the next workshop, we'll do more of these minimum, maximum points and stuff. All right. Does anyone have questions they would like to ask? Everyone wants to finish early. All right. So if you do have questions, hang around and ask. If you're here in person, sign the attendance papers. Otherwise, I will see you all on Tuesday next week. Goodbye, everyone.